Welcome everyone to part 3. In this part, we will continue doing the cruise control or speed control, and today we will actually implement the PID controller. In the previous part, we implemented only the proportional controller, and we have seen the problem of the oscillation that can come with a proportional controller. And today, our target is basically to, as you see, is to have a PID controller that is first of all, converge at the target speed and is more stable and robust than the PID controller. And basically, what we will cover is how to implement that, how to tune the PID controller parameters, and how to do the speed profiling as I'm doing now. So before moving into development, let's take a look again at the formula of the proportional controller. But we have the action ut, which is equal to the proportional gain multiplied by the error at time t. We have seen that the proportional controller at specific level of the proportional gain, it starts to oscillate. This is called the critical gain because we start to see the oscillation. Oscillation means instability. If you are sitting in that car, you want to be happy if the car starts to oscillate around specific speed. So first of all, why would we have this oscillation? What we see here basically is a kind of the formula of this simple or harmonic oscillator. So if we actually take a look at the simple harmonic oscillator, if you just look at Wikipedia, and we see here basically the formula or the model of the simple harmonic oscillator, where we have, let's go there, it's more clear. So what we have basically there, that the acceleration of error, let's say, because x in our case is error, is equal to kind of a gain. Here we have a negative gain multiplied by the error itself. So under a certain condition or certain basically values of k and m, this would lead to kind of harmonic oscillator. So what we want is a damped harmonic oscillator. And if we look here, basically, we see first of all the blue oscillation without any damping. And then we have basically, this is basically the damping constant. And we see if we increase that constant, we converge faster at the zero level. And if we have, for example, the green one, which is a bit lower than the one, or it's half of the one actually. So we see we have a kind of overshooting. Then it will converge again at the zero axis. If we have really high damping, which is bigger than 1, we would see basically it would take longer to converge, but it won't oscillate at all. So basically we have kind of small oscillation. So this is the idea, and this is what we want to have actually with the PID controller, because we have the error that start at 30 kilometers per hour, and we want it to converge as fast as possible at the zero error, with the basically with the least oscillations as possible, because we don't want to have oscillations within the car. And if you look at the damped harmonic oscillator, basically it has this general formula here, where we have the acceleration part, here's the speed part, and here the position part. And here we have the velocity, which is the angular velocity there, and it is basically the angular velocity of the oscillator. And here we have the damping ratio, and this is basically what we see there. And we have seen if we increase the damping ratio, the signal would converge faster at the zero. And if we have, for example, we have 3 type of damping. So if it is basically over 1, it's over damped, which means it would take longer to converge at the target, which is here 0, but it basically more stable. So no oscillations would be observed or observed, sorry. And here we have the critical damped, and this is basically equal 1. So the car, it actually returns to steady state as possible. It is faster than the over damped, and hopefully there's no oscillations at all. And if it's smaller than 1, we may observe some oscillations like overshooting here, as we have seen. So if we look back at the formula of our PID controller, and if we assume that this is the general formula, as I said, of the driven, or actually of the damped harmonic oscillator, and we take the integral of the two sides of this equation, then basically the integral of course, the second derivative would be the first derivative, then the integral of that would be the error itself, and the integral of that would be the area under that curve. So it is basically the integral of the error. And we would have here three parts, and this actually represents the PID part, because this is the proportional part here, this is the derivative part, and this is the integral part. The derivative part always represents the damping. And if we look here basically at the signal, this is the derivative direction. And because derivative represent the gradient of the error. So if the error is decreasing, let's say if it started at 30 kilometer, decreasing too fast, then we would have positive, we would have a negative gradient, okay? Because the next error value is actually smaller than the current error value. So we are getting a negative gradient. And if we add now the action, we add this part which is proportional to the gradient. Here, this part is always in the opposite direction of the error itself. So if the error is, as I said, decreasing, then the gradient would be in the opposite direction and would kind of acting like a damping or braking effect. So it would basically would try to, if it is high as we have seen, it would basically make the conversions too slow, but also it would damp the oscillations. And this is basically why the derivative is important to have it in the PID controller, because it adds more stability and it damps oscillations as well. And the last part, which is the integral part, what is the intuition behind the integral part? So the integral is, as we know, is the area under a curve. So basically, which is the area under the error curve there. It's sometimes when we have a P and so the proportional and derivative controller, we would end up at kind of a steady state like here. And we would have a steady state error, which is basically the difference between our target and our current, let's say, speed here. Now, this basically represents the area at the third curve. So if we have actually the error curve itself, this would have like a steady error. And if we take that area basically, and we add this area to the proportional PID, you would have here now another linear relationship between, or proportional relationship between the integral, which is the area under that curve, and the action. So by adding this term now, we would start to have basically effects that coming from the integral in order to increase the action a bit, which means add more throttle angles. And by increasing that, we'll start to decrease this area, which is the difference between the target and the current speed. So this kind of adding correction to the steady state error at the end. So this is the proportional gain, or the proportional part of the PID controller. The derivative basically acts as a stability, or plays a role of a stabilizer and add damping to the system. The integral part as basically, or plays a role of correction of the error at the end. So if there's kind of steady state error, it tries to correct that. So if we look back here at the game itself, and we basically now we have four different plots. The first plot here on the upper left part is basically the target speed versus the actual speed in green. So the actual speed in green and the target speed is in red. And you see that it's pretty converged well. So we have basically, even when I now kind of changing the dynamic of the car, it's oscillate a little bit, then it converges at the target speed, which is 30 kilometer per hour. So the second one on the right side is basically the speed error. and this is just the difference between the target and the actual speed. And we have the throttle angle, which is basically the action that is coming out of the controller, which also, as we see, is a kind of stable. And we have the speed derivative error, which is basically presenting the damping value, let's say, or the damping effect that is coming from the derivative. So how basically we came to this phase? So first of all, as I said, we added now 3 different plots. The first one you already have seen in the previous graph, which is a speed graph. I basically joined now or combined the 2 graphs that we had before into one graph, which is basically that has the actual speed and the target speed in one graph. You need to give them 2 IDs or 2 different IDs if they are in the same graph. So here we have the target speed and here we have the speed plot. And also what you can do, if you check here the style of the series, basically you have two basically series. So the series ID 1 is a speed plot. You need to make sure that this ID here is the same as in the graph. And we have the target speed, and I just give it basically green for the speed plot and red for the target speed. And this is for the speed plot. We have the throttle angle, the second one, which is basically is coming from the throttle force or the throttle angle. Actually, that is we take it from the C++ code, as I will show you later. That is the second one, and the third one is the derivative. So basically, it's let's take a look now at the C++ code. So the first thing is what new variables I have defined in the header. We have the 3 gains now for the proportional, integral, and derivative gain. So there are 3 float values that we will use later. We have here the accumulated speed error, which represent actually the integral of the error, because the discrete approximation of integral actually is the sum or the accumulation. As I will show you later how to calculate it. And then we have here the previous speed error, which is a kind of memory that we need to calculate the derivative, which is only the speed at the previous step or the speed error at the previous step. The rest are the same. Now, if you go back at the body of this class, we have the begin play, which is at the beginning of the game. We have the 3 now gains. We have the proportional, integral, and derivative gain, which has 0.5, 0.05, and 0.01. So this basically done experimentally, as we'll see later, how I selected the 3 gains. So this is basically now our gain. If we check the main function that is used actually to calculate the actions, which is currently is under update hot strings, we will refactor this code later to make it more professional, as I said before. But now it's calculated here. The first thing we need to calculate the speed error derivative, and here we are using the finite difference method, which is the very simple version of it, and is actually the current speed minus the previous speed error. So the current error, sorry, minus the previous speed error divided by the delta time. And delta time, we get it from the tick function of Unreal, because at every tick we have the delta time that is given to us by Unreal. So basically we can use it here to calculate the derivative. And the previous error at the beginning, it has an initial value of basically 30, which is our initial target error. And then here we will start to update it. So first we calculate the derivative, then we assign the current error to the speed previous error, which we will use in the next iteration to calculate the speed derivative error there. Now this for the derivative part, we have the integral, which is, as I said, is the accumulation, which is just we are summing basically the error, or we are accumulating this, the error multiplied by delta time, which is the discrete approximation of integral. Then we have now the PID controller. Previously we had only the proportional part, now we have the derivative part and the integral part together. Here I added just one condition, as you see, or two conditions to limit the throttle angle, because physically the throttle angle has some limits. It's not unlimited. So basically here I'm just limiting to 1 and -1. -1 is the maximum braking that you can do, and 1 is the maximum speed or acceleration that you can do. And there's the next part are the same. So we are sending this action to the move forward, which is the throttle angle. And basically that's what we are now using in the game to control the car. So we have the proportional, derivative, and integral. Now, next step is to see how I actually selected the three values that we have seen. And as I said, you need to do some experiments in order to select them. So I would start with 0, 0, 0, which means only proportional PID, or only proportional controller. So I would start with very low. So in practice, basically, you need to start with very low proportional gain, and then you increase that proportional gain until you reach the critical oscillation, or basically you might reach a steady state with a steady state error. So it doesn't oscillate, but it has steady state error. Then we'll start to add some either the derivative part or the integral. So if we have a steady state error, which means there's no oscillation, then we need to add some integral gain, because as I said, the integral gain role is to correct that steady state error. If we have some oscillations, we need then to add some derivative gain to basically damp these oscillations. So I'll start with very small proportional gain. And as I said, so 0.01. Let's save. Go back here, compile again. Okay. So with very small proportional gain, of course, the car, basically the speed now is very small, and we see we have very high steady error, which is about between basically 28, 29, or 27, 29. And we have actually oscillations at this. We can see the oscillation at the speed error derivative. We can see small oscillations at the speed target speed and actual speed graph. But of course, we need to increase the proportional speed. So I would put here 0.1, and we compile again, and let's see. Okay, we see now it's kind of reached the critical phase where it has some kind of oscillations, as you see. So it's reaching critical phase where now we have oscillation. So what we need to do is first add some derivative now part. So if I add here 1, because we need to dump these oscillations first. So let's save. Okay, we see that the oscillation, they are damped. Let's see if it will converge at steady error. No, so we need probably to add more damping. Okay, that's probably over damped. Let's add integral. So let's try to correct now the steady error first. That's pretty good, as you see. So what I've done is actually try to play with the proportional integral derivative. And with 0.1, 0.1, for some reason it was not, actually the dynamic was not correct. So I decreased the integral to 0.01 with derivative 0.1 and the proportional gear 0.1. Now we see that it is stable because it's actually doesn't oscillate much and it reached the target speed and converged there, which is pretty good actually. So if we now increase the target speed, let's say, we can see that is following quite good to the target speed. So now it's, 40 kilometer per hour. And if we basically decrease the target speed as well, it also follows that very well. So these three parameters are trial and error, you can see, or they are actually tuned experimentally. Now, if you have the mathematical model or the ODE model of the plant, then you can calculate or estimate them just by solving the differential equations. But if we don't have the plant model, that means we need to deal with the plant as a black box, and we'll actually tune the parameters experimentally as we have done today. Now, this is for this part. The next part now we would do the lateral control, which is the control of the steering angles of the car, which is a bit more complicated but more interesting, of course. And first of all, if you have any question about this part of the video, please put that in the comment. And also, if you find a better configuration parameter than the one I did, also put that in the comment. Thank you very much.